Okay, let me get started again here. Another important data structure I think we need to look at is like the Ethereum blockchain. I don't know if you guys have been working with that or not, but it's like I've been trying to download it, and I've been having trouble getting it to download. So I'll throughout somewhere in the semester I'll talk about that. I missed out on Bitcoin. I was looking at that early on, and my system at home didn't have a large hard drive, like a C drive, because I had a small SSD, solid state drive, so I couldn't download the wallet. But at the time I was playing with it, it's like Bitcoin was like $30 a coin, and now it's over $4,000. So we might want to take a look at Ethereum. I think I'm still trying to learn about it, but one thing I like about Ethereum is you've got these smart contracts that I'm trying to think maybe there's some way I could use that to fund software projects, perhaps. But anyway, I think Ethereum's about $320 now, so I think it's worth looking at. Again, it's like they say that you can go to like a website like My Ethereum Wallet and buy and sell Ether from there. But really, they say what you want to do. I want to download the blockchain so that I can start mining Ethereum. So these are all things that I'm trying to learn how to do. So hopefully as I figure things out, I'll kind of pass that on, and we can try to understand the blockchain and how all that cryptocurrency works. Okay, well, computer-aided software engineering tools. Again, ROSE is the one we'll be using in here. There are others that, like for requirements, you'll see DOORS is used a lot. You can put in a document and capture text out of it, stick that in a database, and then say, here's how we're going to test this requirement, either by a formal test or by inspection or however. There are source code management tools. I thought ClearCase was going to be the de facto standard because, a lot of places were using it, but you almost have to have like a dedicated engineer or two running that. It's one of the nicest ones. It's one of the most user-friendly to keep track of like what source code goes into a particular build. But now we've got CVS. That's a popular one. We've got GitHub now, which is out on the internet. Object Team, Microsoft Project, tools for project management. So you'll run into these if you, it's like if you work on a large software project. These are some languages. Probably the most popular are C, C++, maybe C#, Java. We use Python in the robotics lab. I'm running a project in the robotics lab where we're working with the robot arm. I'm trying to integrate that with my algorithms class. It's like if you have like a plate or a circuit board that you're trying to solder. It's like you have a number of points here. And you got 10,000 or you got 10 million of these things that you need to solder. And so you want the robot arm to move to each of the points. It would be kind of nice, like if you could figure out the shortest path that the robot arm would take, just because robot arms are expensive. So we're working on a Python class now that will move the robot arm to a particular location. And then in my algorithms class, we're going to implement the algorithm to make sure that the robot arm moves the shortest distance. that turns out to be a problem called the traveling salesman problem. It's like if you're a salesman and you have a number of cities that you need to go to, you need to figure out the shortest path to go to all of the cities. And so there are ways that we can not come up with the guaranteed optimal solution, but we can come up with a pretty good approximation. Because it's like as you add cities, it's like the problem gets more and more difficult. Really, the only way you can solve it is by exhaustively searching all of the paths. But there are some polynomial time approximation schemes where you can figure out a relatively quick way. So we're going to build that algorithm, and then we have like a Python class that will read the points that are generated from a file and then move the robot arm from point to point. So that also is a project that I have going on this semester. So the robot lab's on the second floor. I don't know if you've seen it, but it's on the right-hand side on the second floor of Becton. Okay, what else? All right. Big thing about Java. Java is Java and C++ are object-oriented languages. Java is always free. Sun Microsystem, you can get the latest version from them. It is an object-oriented language. It doesn't have multiple inheritance. The one nice thing it does have is garbage collection. Unfortunately, garbage collection is nice because, like, when you create a class, you don't have to worry about deleting it. The Java runtime will take care of that for you. Whereas in C++, if you create a class using the new operator, then you have to delete the class when you're done with it. So, it's a nice thing. And if we look at like a design pattern like the singleton design pattern, that's a nice design pattern to implement. When you're in Java, it's easy. You just implement it, and then the runtime will delete it when it's done. But if you create it in C++ using the new operator, then you kind of have to keep track of the fact that you've created this object from the class, and before you terminate the program, you have to delete it. So again, in here, we'll be working with C++. Ada was an earlier language. There's an Ada 83 that had generics, which is analogous to the standard template library, but did not have the ability to instantiate classes. Ada 95 had that capability. They came out and said that Ada was going to be the language that all government projects will be implemented in, but it just turned out not to be the case. I think the reason it failed is because the tasking and the runtime was built into the language, and they wanted to keep those, as projects evolved, they wanted to keep the operating system separate from the application, and Ada didn't let them do that. One nice thing about it is they had Ada packages where you could separate the specifications from the bodies of the informational strength modules. We also do that with C++, where we will have header files, and then we will have the implementation in CPP files. But it just worked out a lot better in Ada. They actually had, so you could create separate libraries that had the specifications and the bodies in them. So for me, this is a very good language for a large project. The ability to do that really helped in communicating, and you could lock the specifications down in this library, and then you could work on the bodies in a separate package, and having those having the specs locked down kind of gave some structure to the overall project. But you do not see ADA projects anymore. So C was created in circa '69 by Kernighan and Ritchie, working at Bell Labs. I don't have the C book. It's not a block structured language, so that you can't have functions defined in functions like you can in Pascal. So if you ever take systems programming, we'll use the long jump and the set jump functions that allow you to do things that you could do if you had a block structured language. There's a preprocessor, so when you see things like pound defined, there's a preprocessor program that comes along and does some work up front before the compiler executes. There's typing, but it's weakly enforced, so you're easily able to convert between types. It is not an OO language. It's not an object-oriented language. There's no garbage collection, but it is possible to simulate creating objects, and we do that in CSCI5555 systems programming. No garbage collection. This is the book that defines the C programming language. And if you're ever doing systems programming, this is probably the language that you're going to be working in. When you work with DSPs and embedded devices, you want fast performance. So that's why you use C instead of C++. So C++ has nice features like being able to instantiate classes, virtual functions, overriding functions, but those things take time, and that's why you won't find them in like DSPs or places where you need the speed. C++, created by Sue Strope, again, Bell Labs, 1979. It's a close superset of C, but there are things in C that you don't find. There are features of C you need to be aware of. It's things like if you use a for loop in C++, you can say for int I equals 0, etc. But in C, that variable has to be defined outside of the for loop. Variables have to be defined at the top of blocks, and we'll see what those are later in C. But in C++, you can define a variable anywhere. Again, we have a preprocessor. Typing is weakly enforced. It is an OO language. There is no garbage collection, but if you define a class by reference or create a static class, the runtime will take that out for you at the end. So there is a type of garbage collection depending on how you create objects from classes. And we'll go over that later in the class. After you're done learning C++, Scott Myers has a number of classes that are a number of books that help you program in C++. There is a later version of C++ out now with some advanced features, and we're not going to be using that. But if you're interested in continuing your study of C++, Scott Myers is a great author to follow the work of. The Dytel books, I have this book, C++ How to Program. A lot of people don't like the Dytel books, but when I was doing some Java work, I had the Java How to Program. And it's good to tell you, it's good to look at, it tells you how to do stuff. It's like if you need to know how to open a socket and write a UDP packet to a socket, there'll be an example in here that shows you how to do that. So I'm assuming that the C++ How to Program book is the same thing. It just gives, it isn't really so much a how-to, but it just gives lots of well, I guess in a sense it is a how-to, but it just shows you how to do a lot of things, a lot of practical things. So that's worth taking a look at. And a lot of these books, like Dytel, they come out with a lot of editions. So if you go back and get like a previous or a 2 version back book, you can get it for really reduced price. This book was before we had object-oriented programming. I consider this to be a groundbreaking book. It defines what a good module is. If you work with the Unix operating system, there are a lot of their functions give you a good definition of what a bad module is. So they like to pass data by using external variables. They have logical strength modules where you'll pass in a flag that will change how the module operates. And it was like in 1975 that Glenford Myers came out with a book that described what a strong function is or a strong module is. So he defined modules in terms of the strengths. The best is a functional module where you have think of like a square root function, pass in a variable, you pass in a real variable, and out comes a square root. So you can tell what it does one thing. He also defined informational strength modules, which is like the basis of object-oriented programming, where you have a module with the data structure hidden in it, like an abstract data type. The module's hidden in it, and then you have a number of entry points where you can work on that data. So like prior to C++ and Java, we had some types of Fortran, like VAX Fortran, that had multiple entry points, and you could create these informational strength modules. So it's this groundbreaking book, because it first identified informational strength modules. Coupling, the best kind of coupling is loose coupling, where, again, like with the square root function, you pass in a value, you get the answer back. Again, if you're working with Unix, they use external coupling, where you've got this external variable that, it's like you'll call the function, and then it's like you check this external variable to see how the function performed, if there were any errors. So anyway, I'm not going to go into these in detail. You will encounter these if you continue taking classes in computer science. This is the worst type of module. It really doesn't do any one thing. You can tell by looking at the name of the subroutine, A5, that there's really it doesn't really tell you what it does, and it just does a number of unrelated operations. So that's the worst type of module. A logical strength module. The thing is, it has like a one function. Let's see, where you pass in like this access table. You pass in an access code, and you got set all and etc. So you set this code, and you pass it into the function, and then the function can do different things depending on what the code is. And there's a lot of those in Unix. And the problem with that is you pass in a code, and sometimes the parameters are used, sometimes the parameters are not used, and it's just a bad form of coupling. Let's see. Okay, so the best type is is functional strength, where the module just does one thing. So that's okay. You can look at these in the slides and see the example. So objects can be created in non-object-oriented language. You can use templates. You can create a code generator to do it before you compile the module. And what we do in CSCI5555Fall2017L1P2 is we write our modules where the caller holds the data. And so that's a good way to create objects in a non-OO language. And that also lets you create reentrant code, and we'll talk about that later. So there's an example of an informational strength module. There's a table that's contained in the module, and basically there's a number of different functions that you call that operates on the data that's hidden within the module. And so this, in effect, is an abstract data type of a table. And we can do different things to the table. We can set all the entries in the table. We can print out the table, but we don't directly access the table. We go through these functions that are defined. All right. So these are our coding standards. So the first one tells us like what class names will be in Camelback notation with the first letter capitalized, and should be a noun like car or input command manager, input parameters. Variable names is this Camelback notation, but the first letter is lowercase. Very important to get used to using the const keyword. That's a very overlooked keyword, and there are some important things that happen when you use const. Again, it's like as we go through the semester, I'll point that out. One statement per line, even though you can do things like int x comma y comma z equals 15, or put int x equals 15, y equals 13. Let's keep one statement per line. 20% of the line should be comments. I think I'll create a standard header which will go at the beginning of each of the modules. And number 9, Visual Studio is the default interactive development environment. If you would like a copy of Visual Studio for your notebook, send Krishna an email. We're going to make some copies of Visual Studio 2010. It's an older version, but it should be adequate for what we're doing in here. I don't know what do they have in the labs. They have 2017 or something. But you can work in 2010, and you can, it's like when the grader gets it, she can upconvert it. It's like all of these are backward compatible. So if you get a copy of 2010 and do the work in 2010, then the grader can take it and upgrade it, or use 2010 to test it. Okay, so more on this later. And then I think like programming assignments, you turn in a zip file with the Visual Studio project file and a README document to describe the output. And if you didn't follow any standards, why not? And again, any information that you want to let the grader know about should be in this file. So again, when I post the first assignment, I'll give explicit instructions as to what to turn in to get graded. Okay, I'm going to go through the book slides, and there's going to be probably a little bit of repetition, but this should get us to the end. So both of these sets of slides are posted in course documents. keep an eye in course documents, because I will be posting the first assignment in there in a day or two. Okay, so some of this we've probably covered. So this is their software life cycle. It won't stay up. Remember, we talked about requirements, the requirements phase. So here, it's like we have requirements solicitation, where we go out and elicit requirements from the customer. We typically create a requirements analysis document, so they call that software specification. We have preliminary and detailed design, sometimes also known as high and low-level design. Then there's implementation. A lot of times that's called coding and unit test. Testing and verification, delivery, operation, and maintenance. So if you're looking at DevOps, this is like in the development arena, and then after it's delivered, the operational baseline, this is like the ops part of DevOps. Here's the waterfall model. Again, if you're using this model, you do each step one after the other. So you analyze, specify the requirements, do design. Typically there's like a preliminary design and then a high-level preliminary design, detailed design, implement, test, delivery, and then when you deliver, most times there's going to be problems because you're going to introduce errors at each step. You're not going to completely understand the requirements, so that's going to filter all the way down to delivery. So that's why the waterfall model is kind of out of favor, but sometimes you have to do it because, sometimes you get paid after each of the phases. So when that happens, typically there's an outside group that monitors, like at each step, what's being done to make sure that, that there's no misunderstanding of requirements. So there's typically a software quality assurance group that looks, at each of the deliverables that comes out of each phase of the project. This is the spiral model. So really what it is, it's, you have set objectives, risk assessment, development, validation, and really what you're doing is it's like you're continuously doing the waterfall activities. So really, this is kind of like Agile, but well, I guess it's really not, because you're continually working on the software project as a whole, but it's like you're not doing one phase after the other. It's like you're setting objectives, assessing the risk, you develop, validate, set objectives, assess the risk. So again, it's not really like one phase after the other. It's you're continuously working through the software life cycle. And let me So this is a description of what we did for our predictive wastewater management system. I'll show you our life cycle. So this is the life cycle that we use here on the projects that we develop. We start with the conceptual phase, we elicit requirements, and we create a functional baseline consisting of a number of requirements analysis documents and associated UML models. And then we, because it's a highly volatile environment, academia, it's like we have a lot of interruptions, about midterm time. So work grinds to a halt because we have to go through midterm exams, and then we get started again, and then we have final exams. So these agile runs, we try to make these last about from now until week 6 or week 7. So we'll identify the requirements, select a subset of them, do an agile run, and you'll notice here, like we do high-level design, and then we have this extra phase here called procurement. So they don't really show these in the other life cycle models, but on a typical project, we write some of the software, but we also go out and procure software. So we added that in as a phase, and we're looking at trying to find model evolution tracing tools. So as we go through our agile runs, we don't actually do a detailed design phase. It's like our intent is to take the code and have model evolution tracing tools that we can use to go in and reverse engineer the code from run to run, and then identify the changes that happened on each agile run. So, we go into detail more in that in software configuration management. So that's a pretty big research area, coming up with tools to capture the changes that happen in the design baseline. And then it's like as we continue to do agile runs, we build up the project baseline until the point where we can release that to the customer, and that's the operational baseline. So this is what we try to follow in our work here. So this is our life cycle for the projects we do at Fairleigh Dickinson. I think maybe I'll post this for you if you're interested in what we did for this particular project. So we kind of went over like what software engineering is. It's a disciplined approach to the design, production, and maintenance of programs. Again, we looked at a number of tools that assist us in developing the software on time and within cost estimates. And we went over some of the tools that they described there. So what's an algorithm? An algorithm is a logical sequence of discrete steps that describes a complete solution to a given problem, computable in a finite amount of time. So here's let me see if I have this. This is from Intro to Computer Science here. Go ahead. So this is an algorithm that finds the greatest common divisor of two integer values. So the input is two different integer values. The output is the greatest common divisor of the two integers. So you identify the input, you identify the output. So step 1, set m to the larger of the two, set n to the smaller of the two, set g to 1. And then step 2, for I equals 2 to n, do the following. And then, so the thing about an algorithm, it's language independent. So you can implement this algorithm in Java, C++, Python, So it doesn't require a specific language. So you go through these steps, and when you're done, step 4, you can print out G as the greatest common divisor. Or you could return it or whatever. That's why it's in parentheses. But after step 3, G contains the greatest common divisor. We did Euler's method for doing this. This is another way of finding the greatest common divisor. So this is actually the first assignment for Intro to Computer Science. So we're doing a Visual Studio project. So it's an example of an algorithm. Okay, so it's a logical sequence of discrete steps, language independent, and it describes a complete solution to a given problem. And you should be able to tell how long it's going to take to execute that algorithm. So programmer toolboxes, we have hardware, it's like the hardware is the computer and the peripheral devices that the software is going to run on. Software is more than just the program that you're writing. It's the operating systems, editors, compilers, interpreters, debuggers, test data generators, and it's also the deliverables. It's the deliverable artifacts that come out of each phase of the software product. So like a requirements analysis document, you need to control that and make sure that you have the correct version of that, just the same as the software that you're working on. And then they talk about this ideaware, which is a shared body of knowledge. So I've not heard that before, but I'll take their word for it. Goals of quality software, it works, whatever that means. The only way that you can claim that software works is you have to demonstrate that it meets the requirements. And so, it works is kind of an open definition. So so instead of it works, it meets the specified and unspecified requirements that the customer has levied on you. You want to be able to modify it without excessive time and effort. So again, that's another reason why we use design patterns. If you look at design patterns, they are such that it's easy to add functionality to a software product that's been developed with them. And again, reusable, reuse. Reuse is more than just taking the code and putting it into another product. I also think of reuse as being able to take the software and putting it in a test environment so that we can test the software. And again, it's completed on time and within budget. So these are the goals of software and what software quality is. I think Bursoff, the author of our software configuration management book, calls this software integrity. So however you want to call it, this is what we're after. Again, the requirements document, the program specification, the requirements analysis document tells what the program must do, but not how it does it. But there is a caveat here. Sometimes you are told how the program has to do something. So if you're working within an architecture, you are told how the program, to some extent, is supposed to do something. So take this with a grain of salt. Just in general, the requirements tell what the program has to do. But again, sometimes how the program does it is levied on you by the customer. And it's, as they say here, it's written documentation about the program. And it's also a set of, it can be a set of models that model the behavior of the program. So remember, in our life cycle, we have like requirements analysis documents, and then we also have UML models. We won't use those in here, but that part of the UML, again, that's like the use cases and the scenarios and the collaboration diagrams. Those are kind of like the upfront aspects of the unified modeling language. A very important consideration in software engineering is being able to abstract a problem. So depending on where you're at in the building of the software, you have different abstraction, a different abstraction level. For instance, if I'm writing a C program that is running on the Unix operating system, and I want to write some data to a file, well, I'm at a certain level of abstraction with the operating system. And those are provided by a set of functions that I can call. So I can call open, and open will open a file. Well, I just think of it as there's this data store out there. I open it, and then I call write, and I can write records into the file. I can close the file. I can print the file. So I'm up at this level of abstraction. But if I go down deeper and look what's happening, it's like when I write data to the file, down at the lowest level, it's like I'm sending ones and zeros maybe out to this device that has a magnetic platter that's spinning around, and the write head is writing ones and zeros to this device. Well, I don't have to know that. I don't even have to know really, like, it could be writing to a solid state drive, it could be writing to a USB drive, it could be writing to a mechanical drive, it could be writing out to the cloud maybe. And I don't have to know that. It's like I'm working at a higher level of abstraction. So that's, programs are abstractions. When I declare a variable, I say int x equals 5. Well, I think I've got this integer, and I've set it equal to 5. Again, what's going on under the operating system is I'm getting a spot in random access memory where this value 5 is being written as a series of ones and zeros. And actually not even ones and zeros, just different voltage levels out there in this hardware device. I don't have to know that. It's like I can implement an algorithm which is at a higher level of abstraction than the programming language even. So I can implement that high-level algorithm as a high-level language, and then that's all I really have to know. It's like below that, I don't have to worry about what's going on behind the scenes. There can be 10 of us doing the same thing on a Unix operating system, and while we're all working on our problem, it's like the operating system is doing time sharing, so that we each get a slice of the CPU as we're working. So levels of abstraction, very important consideration. You want to make sure you're at the right level when you're working on a program. So they give an example of a car. People have different views of the car. It's like the mechanic. He can be concerned. Like if you have a car and your water pump goes out, it's like all is like there's a problem with my car. So you can take the car to the mechanic. The mechanic knows that the water pump is bad. He just replaces the water pump. He doesn't have to know about the internals of it. He just knows that the water isn't coming out at the right rate, so he just replaces that. So again, to drive a car, you don't have to know about every last detail of the car. It's like you just have to know how to turn the wheel and and step on the gas pedal. All right, visual tools, I don't know what that was about. We talked about information hiding, creating an abstract data type. We want to hide the details of what's going on inside of a module with the goal of controlling access to the details from the rest of the system. And the reason we do that, because we want to be able to replace the inside, we want to be able to replace the implementation inside the module without affecting the rest of the program. So again, if we have a stack that's implemented with an array, that may be fine at first, but it's like the array is a fixed size, so it could be that that'll work okay for a while, but maybe we need to not have a fixed size, so we might want to throw out the array and use a linked list or use a dynamic array, so we can go in and change the internals, and we don't have to touch all of the code that interfaces with that module. Also, programmer can concentrate on one module at a time. So you can pull that module out and give it to a programmer and say, please replace the array with a dynamic array. Again, informational strength module. Each module should have a single purpose or identity. It should be like input command manager. This thing opens a file, reads the data in, and then there are functions we can call to get the data out of the input file. So yeah, again, each module should have a single purpose or identity. If it doesn't, then you need to break the module into more modules so that each one does have a single purpose. All right, so stepwise refinement. It's like when you design a program, it's like you can start from the top down. You can start from the classes that that you're going to need and work up. Functional decomposition this is what we used before we had the object-oriented paradigm. We start with the overall function that the software is supposed to do, and then we take at each step, we decompose that into smaller and smaller functions. And I don't know what round-trip Gestalt design is. I've never heard of that. CRC card is a visual aid that helps you create classes. So if we need a stack, it's like the class name would be stack. Primary responsibility would be to implement the stack abstract data type. And responsibilities, we would have push. Collaboration would be place data on the stack. Pop would be remove data from the stack. Top of stack would be return the data on the top of stack without popping it. Size of stack would be return the size of the stack, etc. So I've never used these that much, but there are places that do. It's just never really. Usually, like when you're using a modeling tool like rational rows, you don't really make use of these that much. Yeah, the way that you look for classes when you're doing object-oriented design is you look for nouns. That is a way to do it. You look for nouns in the specification, and that will give you a clue as to what the classes are going to be. If you're doing functional decomposition, I guess you look for the verbs, and this is how I had this explained to me. But in this in the book we use in CSCI5555Fall2017L1P2, they actually go into like proper nouns, and I don't know, I forget what it's called. I don't know. I think they kind of go overboard with that. So basically, when you're doing design, if you're looking for things to turn into classes, just look for the noun. Just because it's a noun doesn't mean that it necessarily is going to be, but it's just an aid to help you. Most of the projects I've worked on, you have an idea of a model that you're working with, and you express that in terms of the UML, and you go from the UML to the classes. All right. So functional decomposition, again, you are creating modules, but the problem with functional decomposition is, it's like if you're reading and writing data from a file, instead of having like input command manager in one place, you'll have open file over here, read file here, write file here, and then close file here. And just in general, functional decomposition tends to spread the functions of the program all over the program, where object-oriented design clusters those into data and operations that can be used together to solve the problem. 95% of the time, this is the way to go, but occasionally you'll come across a problem where you can't really get a handle on the objects that you would use to model it, so you're kind of stuck with functional decomposition. So there really isn't a right way to do it. And if you look on YouTube, there's this big push towards the negative aspects of object-oriented design, and I'm kind of hard getting on that. It's kind of hard for me to get on that bandwagon because I was around before we had object-oriented design, and I was just champing at the bit to get to it. It's like I was an early proponent of creating multiple entry point modules, and as soon as C++ was available, I was a big proponent of it. So I don't know. I kind of am at odds of just throwing it away. I don't know that their arguments really stand up. I don't know. Maybe they're in the world where their problems functionally decompose. I think I worked on a navigation project one time where it's like it was just hard to come up with objects to model like what happens when an airplane is flying over waypoints, and we just had to do functional decomposition. But it's rare. Most of the time, object-oriented design is the way to go. Yeah. So okay. Yeah. See, you got these. I'm having trouble with it. But it's like so you're doing the functional design where you got get data, print data, and then I forget what this was. This was like acquired data, and so they're spread out. These functions which really should go in one object are getting spread out all over the software. It makes it hard to maintain. You fix one problem, and it's like you'll modify part of this, but then you'll affect some other part of the project, and I don't know. Object-oriented design. In both places, you're decomposing the problem, but in the functional way, you're decomposing it in terms of the functions. With object-oriented design, you're doing modeling. And that's valuable too, to do some modeling up front, get you thinking about the problem, best way to solve it. So this, I think what they're getting at here is this, like, it's a representation of a class. There are different ways to represent classes that we'll be looking at. So, but inside the class, you've got private data, and you've got these functions that act on the data, and then the classes will collaborate. All right. So the classes will have relationships with each other, but the point of having the private data, again, think abstract data type, is you're not allowed to go and directly access the private data. Okay. Program verification is a testing activity where you determine the degree to which a software product fulfills its specifications. So a lot of times when you're done with the requirements document, a good approach is to have a test team start writing test cases for the requirements. So then at the end, the test team can run those tests, and if those tests pass, then you've verified the program against the specification. So again, testing is key. I've heard this before. Verification asks, are we doing the job right? Validation asks, are we doing the right job? I don't know. Maybe that makes sense to you. But anyway, Barry Bain was the author of the Kokomo model, the constructive cost model, which was a software metric used for determining how long a software project is expected to take. All right. Types of errors. At any point of the software lifecycle, we can introduce an error. We might not get a requirement right. Again, we're working with human language, so there's ambiguity. We can make errors in design, coding, a number of different places in the project. The point being, the later an error is discovered, the greater the cost is going to be. So if we catch an error like in the preliminary design, basically what we're doing, we're making a modification to a document. If we catch an error out in the operation, they say to change one line of code in a flight computer costs tens of thousands of dollars. Not because it's a big thing to change a line of code, but it's like when you do it, it's like you have to go all through the validation process again. So you want to catch errors early. And again, this is like some of the rationale of the agile process. It's like if we can do multiple passes through this, it's like we can do a pass through everything, and even if we catch it later in the project, we're not fixing it is not as difficult as if we let that error continue to persist, and then we deliver all of the errors at once. So you want to catch errors early, and if you're not doing agile, then it's probably a good idea to have a quality assurance group looking at the deliverables and reviewing each of the artifacts that come out of the phases. Some terms here. Robustness is the ability of a program to recover following an error. Sometimes, like in our homework assignments, I'll just tell you, we're not going to test for error conditions, so you don't have to worry about that. But then sometimes we will. So if a program is robust, it'll recover from an error. And preconditions, assumptions that must be true on entry into an operation or function for the post conditions to be guaranteed. There might be a range of values that you only have to test for. And post conditions, of course, are after the fact. 3 types of design reviews. Desk checking is tracing an execution of a design or program on paper. Walkthroughs, you'll encounter these on projects where it's like you will code a module, for instance, and then it's like you will have to present the module to a team, and you would be amazed how many errors you can find just by presenting your module. So you can do those, and then an inspection is a verification method in which one member of a team reads the program line by line and the others point out errors. This is the best thing you can do on a project to ensure the quality. If this is all you do, you have walkthroughs and design reviews. The other thing that happens here too is, like, you get the team working together, and you'll learn, oh, well, I need a function that will do that, and you've done it here, and so you discover that during the design review. All right, so I think I'm going to stop here. I think we have a few more slides to go, so we will pick this up the next time we meet. Any questions? So be looking in course documents. I'll have a program posted for you to work on, and it won't be due by next time, so it's like whatever it is, I'll go over it and give you some guidelines, and it'll probably be due the week after next. So thank you and welcome back, and I will see you next week.